Right, okay. So welcome to the second lecture of the Blockchain Course 101. I see new faces here, so I'll just do a little introduction to the society, if you haven't heard of us, and to the course that we're doing. So we are a decentralized society. We started last year in September, and the whole purpose of the society is essentially educate you guys about decentralized technologies, like decentralized web protocols, blockchain protocols. We're now also exploring, cryptocurrencies from financial side. We are running internal research project, also related to portfolio management with cryptocurrencies, and it's led by a fourth-year economics student. So if that's something that interests you, feel free to talk to me after the lecture because there's opportunity for you. Just to give you a little introduction about the course, it's a course heavily inspired by the Polkadot Blockchain Academy course that I attended this summer. And the whole purpose of this course is to essentially build a theoretical foundation for you to understand how essentially Web3 works. So we're not even talking about blockchain right now. We're just talking about all the cryptographic and economic primitives that are behind the blockchain technology. And the course is consisted of 4 modules. The first one is cryptography, the one we're doing right now. The next one will be economics and finance. The third one will essentially connect the dots from the first and the second modules and introduce you to the actual concept of the blockchain. And the fourth module will allow you to get some hands-on experience and essentially build your own blockchain using the blockchain development framework called Substrate. And what also DSOC team thought would be really nice if some of the lectures, ideally majority of them, would be delivered by essentially experts in the field. Hence why we invite lecturers from University of Southampton. Last session we had George, a PhD student. This session we proud to have Dr. Boojoong Kang. The next session we'll have Dr. Leonardo Aniela. And for the first lecture of economics module, we just confirmed to have a professor from a business school who's going to essentially deliver an overview of how cryptocurrencies essentially contribute to the global financial market, which will also, give you a little introduction to game theory and other economic incentives of the blockchain. So, okay, I don't want to take any more of your time because you're here not for my talking, but for the actual lecture. And I'll pass the mic to Dr. Boojoong Kang. Yeah, thank you.
Can you hear me? Oh, good. All right, thanks for the introduction. So welcome back to the Blockchain Course 101 and the second lecture on digital signature. So I'm Boojoong Kang, working as a lecturer here at the University of Southampton and member of the Cybersecurity Research Group. So learning outcomes as a usual lectures. So at the end of this, so you should be able to explain the process of signing and verification using digital signatures. And also you should be able to discuss different use cases of the key derivations. And then lastly, you should be able to compare different types of multi-signatures, hopefully. So outline, we have 4 important topics today. The first one is to understand what is digital signatures. And second is the signing and verification process. And third one is key derivations, and the last one is multi-signature. So let's start with the signature thing. So what is a signature? What is a signature? What kind of signature do you make or write? Please? To verify what? So, your identity. So by signature, you prove your identity, or so where do you put the signature? What was the last time you put your name on something? official document, something you cannot just tell us, right? So mobile contract, Latin contract. So you put the line, you put your name at the end of or each page of the document. For what? Why do you need to put your name on there? Why? Why they're asking the names, your signature? Yes? So you are the person, agreeing with the terms and conditions in the given document, more or less the contract. So here's the one definition from the UN Commission on the International Trade Law. So there are many different functions, not in this slide, depending on the application or document you are signing on. So don't read every lines, focusing on the highlighted in red. So the first one is identification. So you want to identify who you are signing it. So the signature itself. And second one is providing that you are involved in. So the actual person writing the signature. So you are the one signing it, no matter what you sign actually. It doesn't matter. You might be signing someone else's name, right? But it was you writing that signature, whether it was in different names. So another function is the evidential. It was you, although you claim it to be yourself or someone else. And the last one is the signature associate you with the contents of the document, the contract. So you are agreeing with the terms of the conditions, terms and condition of the contract. So there are many other functions, but these are the main functions we usually dealing with when you write signature. So what is digital signatures? So I'm not going to ask you, but it's the same. The only difference is that the digital signatures are represented not by ink, but the cryptography proof. And their purpose are here, given in this slide. So maybe some of you are aware of the cybersecurity property, CIA, confidentiality, integrity, and availability. But there are many other cybersecurity properties that we require. Here we have some of the property related to these digital signatures. The first one is authentication, second one is non-repudiation, and third one is integration. So let's look at one by one. Authentication. Anyone knows about authentication?
Proves that you are who you say you are.
So to prove that, is that that you are claiming to be one, right? To authenticate yourself. So digital signature provide authentication for us, so that you claim someone by writing signatures, and also it proves that it is actually you that claim to be the person that you're claiming to be. So that with the digital signature is given, so the receiver should be able to believe that the message was created by the owner, the actual sender, actual signers. And the second one is non-repudiation. So digital signature you shouldn't be able to generate digital signature for someone else's. It must be you by the technology itself. You cannot forger the digital signature of someone else's. So if there was signature of yours in some document, you cannot deny it. You're the one who signed it, because someone else cannot sign this digital signature. So non-repudiation means that you cannot deny it. If there is this digital signature, so it was you, not someone else, you put the signature, you cannot deny it. You agreed on some terms and conditions, depending on the document you signed on. The last one is integrity. So integrity means the message was never manipulated after you sign it, because this signature will have some mechanism to prove it. The message was the same thing, is the same thing that you signed on. So ensure that the message was never altered in any way. So although they provide digital signature provide many this kind of cybersecurity properties, but digital signature doesn't provide you confidentiality because it doesn't encrypt the message itself. It just provides cryptographic digital signature for it. So you will need to encrypt the data separately after you sign it. Any questions so far? I hope you have full understanding of digital signature from it or the basic concept. Any questions? Okay, let's move on. Now we will look at the process of signing and verification process. But before we go into details, I want to remind you the asymmetric encryption. I hope you remember the last lecture about this. So quick reminder is that in asymmetric encryption we have pair of keys. One is private key, another one is public key, right? And with the given data, so using public key, we can encrypt it. So we call it encryption. Then we get the encrypted data. So the public key is known to everyone because that's why we call it as a public. And if someone sends you a message in a secretly, then they can use your public key to encrypt the message so no one else can see it, but you are the only one who can decrypt it using the private key. The private key is only known to you. No one else has it. So you are the only one who can decrypt this encrypted data using the public keys. So anyone can encrypt the data because the public key is known to everyone, but the owner of the private key only can decrypt this encrypted data. So no one else can see it, but you are the only one who can see the data. But what if I say you can encrypt the data with the private key instead of public key? So as the algorithm itself provide this kind of functionality, you can use private key to encrypt the data. So you will also get the encrypted data. And because the private key is only known to you, you are the only one who can generate this encrypted data, right? No one else has the private key. You are the only one. But the public key is known to everybody, right? So everyone has a public key of yours or someone else's, so that anyone can decrypt this encrypted data by using the private key, which was encrypted by the private key. So anyone can see the actual data in it, but no one else can generate this encrypted data because no one has private key, but only you. So we call this process signing and verification. Again, I'm repeating myself, right? So anyone can decrypt it because public key is known to everyone, but the owner of the private key only generates such encrypted data because the private key is known to the owner of the key. So you can only encrypt it. In other words, you can only sign it. It is only you can generate the signature, sign it, and any other people with the public key who can verify it was actually you signed this key or not. So one example would be asking, you might be asking me to generate encrypted data using my public key, but the message, you can ask me to have it as a hello. Then I can put the hello as a data, and I can encrypt it using my private key. Then I send it over to you. Then you can decrypt it using my public key. Then you can see the actual data written as hello. So you can verify that I'm the actual owner of the private key. So this is the basic concept. And some more details. So data is given. Then we use hash function in the signing process. Why? Any idea? Yeah, so the data, the size of the data can be different, right? Could be short. The length cannot be a problem if it's short enough, but if it's too large, it will take too much time to encrypt it, right? So we want to have a fixed size of the signatures. So we use one-way hash function to transform the variable length data into the fixed size data. So we get the same size of the hash all the time, no matter what the length of the data is. Then we use the private key to sign it. Then the actual outcome is the encrypted hash value of the data. So we call it as a digital signatures. Okay. Then we just attach it to the data. Then it becomes the digitally signed data. So this is the process of signing. And then using public key, you should be able to decrypt the digital signature to get the hash data. Then also you can use the same hash function to get the hash of the data you received. Then by comparing it, you should be able to tell whether data has been manipulated or whether the digital signature was invalid or valid. So in case of data has been manipulated in transit, then the hash value of the hash function will be different. Or if they use different private keys, then the outcome of the decryption of the digital signature will be different. So you will get different hash value in either case. So this is how you can verify the digital signature. So that proving that this data is signed by the particular person with this private key, and the data has not been manipulated in any way. So providing authentication, integrity, and non-repudiation, because you are the only one who can generate these digital signatures. But another point is that data is not encrypted. So you might want to encrypt this data segment again for the confidentiality. Okay? Any questions so far? Going smooth? Not so difficult, right? So we will touch two more points. We'll take a little more time that we spend. Let's move on. So let's think about an e-commerce application that you want to develop, and you want to use a new address for every transaction you are having or you are making. So as an example, for different shopping cart, you want to give different address to make a payment or to receive the payment. How can you do that? Using Bitcoin. How can you assign new address for every transaction? Yeah, maybe you are thinking about the current technology in Bitcoin, what kind of function you can use. But the thing is that you can generate number of keys, right? As many as you want. Like if you are dealing with 1,000 transactions per day, then you generate 1,000 keys and use them. And next day, you generate another 1,000 keys, right? You can keep generating keys for new addresses. Not using advanced technology in Bitcoin, because I'm going to explain the advanced technology. So in a simple way, you can generate the keys as many as you want. But when you have simple approach, there is some limitation or drawbacks. So generating keys all the time doesn't sound right. It doesn't sound all right. It's hard to maintain the key. It's very difficult to generate keys all the time, and your service might run out of keys per day. So you estimate I will get 1,000 keys per day, and you generated 1,000 keys, but actually you got 2,000 transactions this day. Then you are losing 10,000, another 1,000 transactions today. So it's hard to maintain and meet these requirements accordingly. So it's not a great idea, right? So then we want to generate keys without any conditions, without any limitation. We want to have a without any limitation, we want to generate keys. So here's the technology provided by cryptocurrency called hierarchical deterministic wallet, HD wallet. So it's in BIP 0032. So as shown in the figure, you see many keys being generated, actually derived. So in a structured manner as a tree. So the keys are being derived from the upper layer keys. If you see it as a tree, then only one thing you need to manage is the master key or the seed. You don't need to actually manage the other keys because you can derive automatically, deterministically, no matter how many you want, how many layers you want. Yes?
Is there a set number of children keys that can derive from one master key? So, like, for example, you've got 4 there, but you like.
So your question is there any limit for the number of keys can be generated from the master key?
Right. Obviously, you've got
So you're wondering, you understand there's no limit for the depth, but is there any limit for the breadth? So limitless, there's no limit. But practically, they might limit it, right? But theoretically, there's no limit. You can make any keys, any number of keys that you like. So you are wondering what's the mechanism for deriving these keys. So that's a spoiler. It's gonna coming up next slide, okay? So now I see people excited that, sorry guys, that you could generate keys without any limitation. So in this structured manner. So one key generated from other keys, you can generate without any limitation to an infinite depths. So the advantage is obvious. You know, you can utilize in different business cases, use cases, application. Here are 2 examples. So the tree structure looks like some sort of organization, right? And the different purpose, you can use the different addresses, set of addresses for different purpose. Here's the example given is you can use the branch of sub-keys for receiving incoming payments or different branch for receiving changes from the outgoing payment. Or the last example is, so you can allocate different branches for different department or subsidiaries and different functions or any different accounting categories. So you can design the tree structure simulating your purpose or your organization. So then let's look at how we can create this wallet and how we can derive the keys. Actually, the cryptography algorithm is based on electric curve, but I'm not gonna go into details about the algorithm itself. So I give you the reference. So if you are really interested, go ahead and have a look, okay? But anyway, I will try to explain the concept. So to create this HD wallet, you need a random seed in length 128, 256, or 512, any length you like. Then using this seed, you could generate master key and the master public key. And also you get the chain code. I will explain the chain code later, but anyway, you get the pair of the keys in asymmetric encryption algorithm. So then by changing this seed number, you will get different keys, right? Then you only need to remember the keys, the seed. Then you can always recover the master keys because the function we used is the one-way hash function. It will give the same output if you use the same input, right? The hash function is that. But here's another trick here, is that the random number is a number in 64 byte, right? How can you memorize number in 64 bytes? Probably difficult. So the way you could memorize is that we represent this random number into code words called mnemonic code words in a text. So you can represent this number into the word. Then you just need to, still it'll be difficult to memorize it, but it's better than memorizing random numbers, right? It's human readable. Or you could select this word randomly from a dictionary and translate into numbers based on some mapping table. Then you will get this random number, and then you can use it for generating private keys. So either way, you can associate with this random number with this human readable text for your convenience. I will go into more details in the next slide. And the point is that the only thing you need to manage is to get this random seed. Then the rest is automatically generated to get the master key. So this is how you created the HD wallet. And the mnemonic code words, you can either translate the random number into this code word, or you can select the code word randomly and translate into random number for generating the keys. So it is recommended to use or select 12 or 24 words from the mapping table provided by the VIP 039. And then usually we apply more than 2,000 rounds of the hash function to make it difficult to predict. So it is pretty random. So you could use your own phrase or any random data, but it's not safe because you cannot make pseudo-random words. It's very difficult to generate pseudo-random words in 12 or 24 words. So it's recommended to use the English dictionary provided by the VIP, or use pseudo-random number generator. Okay, any questions so far? Okay, then how we can derive keys? Now we have the master keys from random seed. Then there are a number of different approaches for deriving keys from key. So first one is you are deriving the private key from private key to private key. So you have a parent private key here, then you can get the public key as well. Then what we want is to have the child private key from this parent private key. So then we use the one-way hash function again. Then input is the public key, which is derived from the private key, and also the chain code. So in the previous slide, when you generate, we get the chain code as well as a outcome of the hash function, which is more or less random numbers. So the reason why we use chain code is as entropy, you want to generate different keys. If we don't use this, the private key will be always same, then you will get the same output all the time. But the chain code is different, so you will get different private keys. So it is some sort of sort, but also can be regarded as another part of secret. So sometimes we call this private key with the chain code as extended private key, or the combination with the public key and chain code as a extended public key. It's not important, but anyway, it is working as similar to the sort when we hash any input. So the index number is about how many children do you want to have. So by having more index number, the range, you can get more children in the next layer. And how many repeat this algorithm, then you get the more depths in your structure. Then by using hash function, you get the random numbers. It will be the private keys, and you should be able to generate public keys as well. And you also get the chain code. And using these three information, going back here, so use the child key as a parent to the next generation, so you can continuously generate keys after in different generation and generation. So indefinite depths. And by using larger range of the index number, you can broader your family in one generation. Okay? So this is the concept. So it's another difficult concept, but this is the process we generate private key from the private key. But you notice that we use the public key for generating it. And then public key should be public, meaning is that everybody knows it. But when we use the information, we might not want to use some information public when we generate some information private. So you want to make it more difficult to predict it. So instead of using public key, we can just use private key. So we called it as a hardened child key derivation. So there's some more reason why we use this structure, but simple explanation is that because public key can be known to everybody, and we don't want to use some information that everybody knows when we generate the private keys, right? So that instead of it, we use the private keys. Anyway, so then use case of these child private keys, where we can use these keys. So private keys can be used. We can get the public key. We can get the public key for the private keys, obviously. Then we can generate the addresses. Then we can use different transactions. And as we seen in the example of the HD wallet use cases. So we can have different branch of subkey allocate to different purpose and different departments if it's organization. And one aspect is that, so the reason why we want to use more address is to anonymize yourself in the network. So when you are making a payment using same address, then someone else can see your spending habit, right? Then can maybe identify you as an individual. So there might be a privacy issue. So you don't want to reveal any information like that. So it is a use case when you want to anonymize yourself on the same network or on a different network by using different keys. So generating different private keys allow you to use different Bitcoin addresses. However, because keys are being derived from the parent keys, if you lose one of the parent keys, then you will lose all the children keys that you generated from this private key. So you better to be careful maintaining the higher layer, the key in the higher layer. So we could also derive the public keys without generating any private keys. The similar manner, so using public key and chain code and index number to have more different number of children, and then you can get the public keys, not a private key. So why do you want to generate more public keys, without any private key? What can you do with the public key, or what cannot you do without the private key? So we have different function from different keys, public and private keys. What can you do with the public key? In generally, public key, you can encrypt the data. Yeah, but then let's think about the case in Bitcoin, the cryptocurrency. What can you do with the public key?
Verify the sender.
To verify sender using public key. To verify. Then after you verify, what you want to do? Why do you want to verify the sender?
You know who you're sending your money to, let's say.
So to make the money. So you want to send the money to the right person, not someone else. So you want to make transaction. So you need a public key when you make payment. So then more address that someone else has, you can receive different payment from different sources. But private key, then why do we need a private key? So we use public address. Mm-hmm. So you are the only one who can encrypt the message. So what that means in the cryptocurrency world. So it's only you can send the money because it's only you can sign it. Without signing it, you cannot make payment, right? Because you cannot prove it is actually you own the money. So the private key, the purpose of the private key in the blockchain world is allow you to make the payment, right? So without private key, you cannot make any payment, although you have the funds in your wallet. So generating public keys, meaning is that no private keys, meaning is that you cannot make payment. But you only have public keys, meaning is that maybe still you can receive the monies, but you cannot spend that. It's rare, right? It sounds, why? I want to spend my money. Why wouldn't I want to spend my money? But there are some use cases. You want to stop some owner of this address spending money on it. You just want to allow them to receive the money. So I'm the owner of some company, and you are my employees, and I give you the public address to go out, sell some product, and receive the money. I don't want to give you private keys, right? Because you'll be spending my money. You should be able to only receive the money, right? Receive the payment using the public keys that I give you. But I don't want to give you my public key because I want to see who is selling how much, right? So I want to give you different public keys so you can have different, the public address, the Bitcoin address, but you cannot spend it. So this explains this case. So public key only deployment. So no private key. You can only receive it. Yes?
Can you use a master's private key to essentially send money from the right child to the public keys?
So your question is, so whether master key can be used to derive the corresponding private key for making the money in that different wallet. Yes. Because anyway, the public key is essentially from the private key and the master keys. So it's only a matter of time when you decide to generate it or not. It's already there actually, right? You just don't actually generate it, have it in your data. Actually, it's there. It's already fixed. When you have the seed number is there. Okay. Great. Last one. Any questions so far? All right. The last one, the multi-signature. Now, so the case we so far talked about is one person making payment and one person receiving the payment. But there's a use case, some multiple parties making some operation together. So we want to allow multiple party to control, some joint operation together instead of one doing everything. So then for this signature, we can simply use number of private keys to generate number of digital signature for one data, for one operation. Then we attach to it. Then we can verify using the number of public keys to verify that all party members allow it. Yes?
Is it the same public key or same private key or multiple different?
Yeah, although so your question is the private key are the same or not, right?
Are you just using the same key multiple times?
So you're using the same key for the multiple times. We could do so, but there's no point for doing it, right? Then you'll be having same signature in more than once, right? There's no point for doing it, but you could do it, right? But I wouldn't stop you doing it. Anyway, so although the slide shows the same color, it's different keys, okay? So different member will have different pair of keys, their own keys, right? So let's say 10 people having 10 different pair of keys. Then you'll be using different private keys for signing it. Then you'll be generating different signatures, which is belong to each member of the parties. So that by verifying the individual digital signature using the individual public key, then we can verify that all members of the party agreed on that data or document or contract. So this will be a very naive approach, generating, using different private key, generating different signature. And the reason why, then you need to verify one by one. If it's 1,000 people, I don't think we will have this kind of case, but anyway, it takes time to verify it, 4 times at least in this case. What if there's a way that we can somehow combine the all signature into one, so that we don't need to verify one by one, but we can verify the one single signature using some global public key. So we can only verify one signature using one public key, although it was signed by number of private keys. Then we can save our time for verifying the digital signature, and the size of data will be less, because in the naive approach, we should have 4 different digital signature, but in the aggregate signature, so-called, we can only include the one global signature, right? So aggregate signature allows M signatures from M distinct message, even M distinct message. It doesn't need to be same message from N distinct signers. So you could have number of parties, but the size of data at the end generated is the same as the one party signing the document, and the verification process will be more or less same. But actually signing process takes a little bit more time because individual party all needs to sign it, and we need to combine them. Any question? So I think this is one last slide. So another type of signature. So before multiple signature, we talked about one person signing, one person verifying, and we talked about number of people signing all together. Let's say if there's N people signing, and N people verifying it. What if you want to subset of people could verify or sign the signatures? So there might be use cases like this. One of 2. So a cash joint account between partners or between 2 friends. So anyone can put the money in the pot, but anyone can use it anytime, so that one of signature should be sufficient for allowing making payment from this account. So although there are 2 parties involved in this account, so 2 signature, 2 pairs of key will be needed for different members, but anyone should be able to make the money, make the payment. So one signature should be enough for making the payment. And the second, a joint saving account. It's more serious. It's not a small money. Now, we don't want to, any of the member can just spend it. We want to make sure that all the member in this joint account agree on that when we're spending money from this account. So we ask to all of the member to provide the digital signature. And another one, 12.3. So imagine that there's 3 directors in board, and we want to make sure that majority of the director should agree on that some spendings. So we don't need to have all 3 agree, but we only need to have two directors agree on some spending. Then only two signatures will be required for signing and for verification. So we can put a threshold, how many parties needed to sign to actually make the payment from the joint account. So it could be 305, 509, 609, 608, depends how you could design it. And something interesting use case is 1 or 304. It's not 1 or 3 or 4. 1 case and the 304 case. So 1 is with me, so I'm the primary owner. So this is my own funding, I want to use it. So I will use it anytime as I wish. But in case I lost it, you know that when you lose your Bitcoin keys, you cannot use the fund, it goes away, right? But to make secure, you generated 4 keys, and then you hand over those 4 keys to your trusted friends or trusted organizations. You are not using these 4 keys. You were using the primary keys, but you lost it. But to recover this fund, you could ask those friends or organization to recover the funds. Then you only require 3 of them, allowing you to recover it. So this different set of keys can be used as a threshold signature. So example would be you can open up a new account, and by using 304 threshold signature, you could move all the fund to the new account. Then you recover. You are not recovering the key though, but you are recovering the fund that you already owned. So there will be more different kinds of combination of the threshold signature you can think of. And there are many more use cases. So threshold signature is another type of the multi-signatures. So that's it. We look into this signature. So meeting authentication, non-repudiation, and integrity. And we also look at the process of the signing verification. Then we cover the key derivation and different multi-signatures. So I'm happy to have some questions. Any questions? Yes?
So for key derivations, let's say you derive all these, one stack keys, you then lose them all.
Lose them all.
But then you still remember the 12 to 24 random words you used. What's the process of recovering those keys? I guess you just regenerate them again, and then just check the hashes match.
So your question is about what if we lose all the children keys in different generation? Then how can we actually recover those keys using the 12 or 24 words that we memorize or put it somewhere, right? You can just repeat the process because there's no other random number that you need. In the creation of the HD wallet, the only input is this seed number, and seed number can be represented in the word and represented back to the random number from the word. So assume that this is the one you shouldn't be, lost. If you lose this, doomed. As long as you remember it, there's no other input. Make sure that you use the algorithm you used, that run it through it, and remember how many index and how many depths you were generated. Then you will get the same keys because there's no other random numbers used. This is only random numbers. Does that answer your questions? Okay, any more? Yes?
Questions about multi-signatures, especially the use case for recovering for the lost key. So that would also imply that if, let's say, I generate 4 recovery keys and give it to so-called trusted parties, that at any point those trusted parties can essentially just steal my funds.
Sure. So that's why we say your question is whether in the case of threshold signature, generating backup key as a threshold signature, then you hand over your key to some other party, then the party can steal your funds, right? Yes. So that's why you hand over the key, something you can trust. And they need to collide because 304 threshold signature, meaning is that three out of 4 should collide to steal your money. Not only one single person can make the payment from the fund. That's why you generate multiple keys.
Then to solve that issue about not getting 3 people to steal your money, why don't you just hide it somewhere instead?
So your question is, instead of giving away the key, hide it.
They're giving it to people.
Mhm,
why don't you just hide it instead?
So for the backup, there are many different strategies, right? You could have it different copies on your own, or you could have it copy someone you can trust. Like imagine about the keys. So you could have a key at your friend's home, something you can trust, or your parents' home. I mean, you wouldn't do it, I know, you wouldn't do it. But the more backup you have, it's more, I wouldn't say safer, but there's more chance you could recover it, right? So you could hide different keys in some other places. Yes, it's possible. But the way how you think which one is better is up to you, right? But there's a possibility, as you mentioned. Yes?
But at the same time, by giving away backups, you be exposed to a risk, right? Because those people could also access your fund. So if you, for example, give it to your uncle and you have a problem with your uncle, and then your uncle, decides to access those funds.
So the question is about how actually you can trust
Like
the parties, right?
Sword, right? That you need to, each person perhaps needs to evaluate.
So that's why we make sure that we generate different keys, not using same seed numbers.
Yeah.
So this case is you get the one primary key on your own, then you use different key generation 304, you separate them, then you just use it for recovering the funds. So hand it over to someone else. So they won't be able to get your key.
Okay, so 3 of the 4 backups will need to join together in order to access your fund.
Yeah.
Okay.
Right? Any more questions? All right. Okay, then thank you so much.
Thank you very much. Again, thank you guys for making it today. Again, due to weather conditions. Do you have any questions for me, like about the society, about the course? Feel free to ask. If not, again, you can always find me on Discord. Just drop me a message, any questions, any project ideas, any kind of initiatives you want to do. You're always welcome to reach out to any members of the society and, discuss them. But again, thanks for making it today. It would be nice if you can, again, spread the word, share with your friends, because there are going to be even more exciting lectures coming next week and week after. All right. Thank you, guys.